So far, we've been talking pretty generally about cryptographic systems and focusing primarily on encryption concepts, but not decryption. It makes sense that if you're sending a protected message to someone, you'd want your recipient to be able to decode the message and read it, and maybe even reply with a coded message of their own. So let's check out the first broad category of encryption algorithms and dive into more details about how it works, along with some pros and cons. When we covered Kirchhoff's principle earlier, do you remember which component of the cipher is crucial to keep secret? That's right, the key must be kept private to ensure that an eavesdropper wouldn't be able to decode encrypted messages. In this scenario, we're making the assumption that the algorithm in use is what's referred to as symmetric key algorithm. These types of encryption algorithms are called symmetric because they use the same key to encrypt and decrypt messages. Let's take a simple example of a symmetric key encryption algorithm to walk through the overall process of encrypting and decrypting a message. A substitution cipher is an encryption mechanism that replaces parts of your plaintext with ciphertext. Remember our Hello World example from earlier? That's an example of substitution cipher, since we're substituting some characters with different ones. In this case, the key would be the mapping of characters between plaintext and ciphertext. Without knowing what letters get replaced with, you wouldn't be able to easily decode the ciphertext and recover the plaintext. If you have the key, or the substitution table, then you can easily reverse the process and decrypt the coded message by just performing the reverse operation. A well-known example of a substitution cipher is the Caesar cipher, which is a substitution alphabet. In this case, you're replacing characters in the alphabet with others, usually by shifting or rotating the alphabet a set of numbers or characters. The number of the offset is the key. Another popular example of this is referred to as ROT13 or ROT13, where the alphabet is rotated 13 places. But really, ROT13 is a Caesar cipher that uses a key of 13. Let's go back to our Hello World example and walk through encoding it using our ROT13 cipher. Our ciphertext winds up being URYYB JBEYQ. To reverse this process and go back to the plaintext, we just perform the reverse operation by looking up the characters in the output side of the mapping table. You might notice something about the ROT13 mapping table or the fact that we're offsetting the alphabet by 13 characters. 13 is exactly half of the alphabet. This results in the ROT13 cipher being an inverse of itself. What this means is that you can recover the plaintext from ciphertext by performing the ROT13 operation on the ciphertext. There are two more categories that symmetric key ciphers can be placed into. They're either block ciphers or they're stream ciphers. This relates to how the ciphers operate on the plaintext to be encrypted. A stream cipher, as the name implies, takes a stream of input and encrypts the stream one character or one digit at a time, outputting one encrypted character or digit at a time. So there's a one-to-one relationship between data in and encrypted data out. The other category of symmetric ciphers is block ciphers. The cipher takes data in, places it into a bucket or block of data that's a fixed size, then encodes that entire block as one unit. If the data to be encrypted isn't big enough to fill the block, the extra space will be padded to ensure the plaintext fits into the blocks evenly. Now, generally speaking, stream ciphers are faster and less complex to implement, but they can be less secure than block ciphers if the key generation and handling isn't done properly. If the same key is used to encrypt data 2 or more times, it's possible to break the cipher and to recover the plaintext. To avoid key reuse, initialization vector, or IV, is used. That's a bit of random data that's integrated into the encryption key, and the resulting combined key is then used to encrypt the data. The idea behind this is if you have one shared master key, then generate a one-time encryption key. That encryption key is used only once by generating a new key using the master one and the IV. In order for the encrypted message to be decoded, the IV must be sent in plain text along with the encrypted message. A good example of this can be seen when inspecting the 802.11 frame of a WEP encrypted wireless packet. The IV is included in plain text right before the encrypted data payload.